have following the discussions here. Great. So, welcome everybody. Welcome, Amy. It's really great to have you here. I think, many of you know Amy really well as a game theory, reinforcement learning researcher for many years now. Well-known papers in empirical game theory, agent-based economics and trading, multi-agent learning, and I saw many other topics as well. She's a professor of computer science at Brown University, I think for quite a while now. And today she's going to talk about some joint work with, I think, Dustin Morrell and a few others. But Dustin is here as well. Hey, Dustin. On learning equilibria via regret minimization in extensive form games. So Amy, take it away.
Thank you so much, Carl. Thanks for the invitation. I appreciate it. Thanks for the kind introduction. So yes, I'm going to talk about learning equilibria via regret minimization. And not only in extensive form games, I'm going to give you the history also in normal form games. So I've been thinking about this problem for, I don't know, probably 2 decades at least. And, a lot was known about normal form games, I would say 2 decades ago. And a lot more has been discovered very recently about extensive form games. And so we will hear about that today. As Carl mentioned, this is joint work with various people. Most of it is from Dustin Morrell's PhD thesis, which should be coming out any day now. And in addition, his advisor, Mike Bowling, and Ryan, and Mark, and Rika, and James, many collaborators and contributors. So thank you all. All right. So I think everybody in this audience knows very well that AI has been playing games and learning in particular to play games well for many decades. We can see here in the top left, Arthur Samuel playing his first machine learning. Maybe he coined the term machine learning, playing his checkers game, his machine learning checkers program, playing a game against it. Then we move on to Jerry Tezzaro, who many of us probably know, who wrote famous for TD Gammon, his learning program in the early 90s. Playing top backgammon, we see Garry Kasparov in the bottom right playing against another IBM product, the first 3 all IBM products, Deep Blue, and finally Lisa Dahl playing AlphaGo. So these were tremendous successes in mostly complete, I think all complete information games. We are also very interested in recent successes in harder games arguably harder, of incomplete information or imperfect information. So we've also seen successes recently in poker in particular, and I list 4 examples here. I am sure there are more. So again, these games, we don't have complete information. We don't have perfect information. And so they're arguably harder. But there was in 2007, I believe, a breakthrough in this area of incomplete or imperfect information games called counterfactual regret minimization. And it's been tremendously, tremendously successful and a key to many of these poker successes. So what we'll do today is we will talk about counterfactual regret minimization and a generalization for extensive form games, but in particular, that is a way to understand non-zero sum. So poker generally is mostly zero sum, and we will be talking about non-zero sum extensive form regret minimization, a generalization of CFR. So just so everybody's on the same page, here's a normal form game, here's an extensive form game. So I'll be using this game from Wikipedia, Chicken. These are the Wikipedia payoffs. It's a game of chicken and dare. So you know this game. It's where these, 2 macho guys are driving driving at one another and, trying to impress the girls. And, one of them might veer off or not. And of course, if they smash into each other, the payoffs here, they're only listed as 0. They're probably more dire than 0. But that's when they drive into each other. So you want to, the best thing to do is to have the other guy veer off. He plays the chicken and you win the dare. So that's the outcome where, one of these asymmetric outcomes, dare chicken or chicken dare. And whoever's the one that, keeps going straight when the other guy veers off, that's the best thing that can happen. Okay, so that's a normal form games, keep in mind. And on the right, we see a picture of an extensive form game, which I have lifted from this location, which I think you can see is Science Magazine, and probably some of the people who drew this picture are here in the audience. So the point here is that we have, first of all, this is a small variant of poker. So we have chance making the first move up here. So chance is dealing some cards. And then we have player 1 playing at these nodes here, player 2 playing at these nodes here. Here we see that player 1 cannot distinguish. This line is indicating what's called an information set. It means that player 1 cannot distinguish between these two nodes. So cannot tell. They know that they got card 1, player 1 was dealt card Q here by the 1:Q. But they can't tell if player 2 got the jack or got the king. Okay, so that's why these two nodes are linked together in an information set, because from player 1's point of view, they are indistinguishable. Okay, so here's a sample extensive form game. You see all the payoffs listed down here at the bottom, and the players move in progression. So player 1 gets to move where it's player 1's turn, and player 2 gets to move where it's player 2's turn, and then finally, payoffs at the end. Okay, so one important point, sorry for the very poor quality of this picture lifted from Wikipedia late last night, but one important point is that extensive form games are, in a way, you can view them, you think of them, compact representations of normal form games. So we could, if we wanted to, blow up an extensive form game and write it as a normal form game, but we don't want to do that. That's an expensive operation. You can kind of see that in this picture, which is that there are 4 payoffs listed here, 4 pairs of payoffs listed here, and there are 8 listed in the normal form representation. Okay, so we prefer to work with extensive form games as trees and not to think about them as normal form games. Okay, great. All right, so here is our learning model. So we will imagine that we have a learner who is playing a game, extensive form, normal form, whichever. And so here's our learner. He has a policy he's abiding by. He's player I, and his policy is indicated by pi. And at time t, he's using policy pi it. So input to the game are his policy and all the other players' policies indicated here by pi minus it. So all of that is input to the game, and out pops a utility for all of the players, but in particular, we're interested in the utility for player I, which is sent back to the learner to learn from. So from player I's point of view, all the other players and anything else in the environment, maybe there's some stochasticity in the game or whatever there might be, all of that is all sort of, bundled together as an environment from the learner's point of view. All right, so here's our learner giving his input to the game, everybody else as well, and out popping the information that he gets about his utilities for playing this policy. So that's how our learner operates, and this is what regret minimization is. Regret minimization can be also understood as, we've recently been calling it hindsight rationality, because it's sort of a way of kind of looking back on what happened during the game and making sure you don't have regret, you don't, sort of wish you had done something else in retrospect. So here's our learner. Our learner is playing a different policy every day, pi I1, pi I2, and so on, and accumulating utilities for playing that policy against whatever the opponents are doing. And now we consider a potential deviation. So that means that the learner could have done something else. And in general, there may be a lot of possible deviations. Each of them will indicate by a lowercase phi, and there's lowercase phis in the set of capital phis. So again, there could be a whole bunch of them. So we imagine that the learner's strategy on day 1 is transformed from pi I1 to phi of pi I1. So we apply this deviation function, and we get something else that we could have done. And then we apply it on day 2, and we apply it on all the days, and we accumulate the utilities for the deviation function. So what would have happened had we applied this deviation every day? And what we're looking at here is an objective, which is to say that the rewards that the learner achieves cumulatively through time, capital T, should be at least as good as any of the possible ways in which we could have applied a deviation function. So any of the possible ways in which we could have deviated to something else in this set, capital phi. So our rewards from the learner should be as good as the best possible of all the deviation functions up to some small vanishing error. Okay, so hopefully that is clear. So we have a set of possible deviations, and thinking about any of the things in our set of possible deviations, there's nothing that the learner wishes they had done instead of following, that's better than any of, it's as happy, it doesn't have regret for not following any of those deviations. Okay, so hopefully that's clear. That's our goal. Good. All right, so I now, with that framework in mind, want to take you back in history a little bit to what we knew about normal form games. I think I said 2 decades ago, but we're even beyond that, quite a while ago. All right, so what did we know 25 years ago? So we basically knew how to do no regret learning in normal form games already actually in both zero sum and in non-zero sum games. So what do I mean by that? Well, first of all, there are many, I should have mentioned, there are many algorithms that achieve no regret in this sense. So you probably, I'm sure, have heard of them, follow the regularized leader and hedge, and there are many, many of them. But back in 1996, Freund and Shapiro also noticed that there was a connection between no regret learning, these no regret algorithms, and applying them in a setting where you have multiple agents using them simultaneously. So multiple agents playing a game where, let's say in a zero-sum game, there are 2 players where both of them are using, say, hedge, both of them using a no-regret learning algorithm. And so in particular, they observed that if you are both using no-regret learning algorithms in a zero-sum game, that you get convergence to a minimax equilibrium in that zero-sum game. And in non-zero-sum games, by the way, this is generalized to a coarse correlated equilibrium. Around the same time, Foster and Vora noticed that if you apply a different kind of algorithm, so Freund and Shapiro's algorithm is called a no external regret algorithm, and I'll explain to you what that is in a little while. But Foster and Vora invented what we call it now a no internal regret algorithm, which is a little bit different, I'd say a little bit stronger. And the no internal regret algorithms in non-zero sum games converge to what's called correlated equilibrium. Okay, so I'm going to be defining all these terms more precisely, but for now, what you should remember is no external regret gets you coarse correlated equilibrium, and no internal regret gets you correlated equilibrium. And this was known 25 years ago in normal form games. Great. So one thing that I did a couple of years after that was sort of talk about those specific results in a slightly more general framework, this phi framework. So in other words, what we did was we defined a continuum of regret algorithms for any arbitrary choice of phi, meaning any arbitrary choice of deviation. So one choice might be external deviations, one choice might be internal deviations, but we had arbitrarily, whatever your set of deviations are, we can get that no phi regret learning will converge to what we called the set of phi equilibria. Okay, so this is just a slight generalization of what we had before for arbitrary sets of deviations. So one thing we should note is that sort of no internal regret was sufficient in this setup, in the sense that it converged to correlated equilibrium, and there was no way we were going to get anything stronger. We could try to throw more and more deviations into our set and think that if we competed against more deviations, we'd get to a tighter solution concept, but it turned out that that was not going to be possible. So internal were sufficiently strong for this framework. And I should also mention there's a bunch of qualifiers, which is that this convergence I'm talking about is kind of, it's not convergence necessarily in the usual sense. It's not like those policies eventually converge to exactly a correlated equilibrium. They converge on average. So the empirical distribution of self-play is what converges to the set of correlated equilibria. All right, so that's normal form games. Okay, so now enter extensive form games. So in 2007, I've already mentioned, big breakthrough, counterfactual regret minimization. So the idea was that you could achieve external regret in zero-sum extensive form games efficiently, because in the kind of a default algorithm. So again, so now coming back to what I said with the compact representation of the normal form games and so on, you might have thought, well, let me take my extensive form game, convert it to a normal form game, and run my external regret algorithm, and there I will have I can already do extensive and external and internal regret minimization in extensive form games. So we can't just do, we can, but it would be too expensive. We don't want to do that. Okay, so we don't want to just apply the conversion to normal form games and run the algorithms we have. We want to be smarter about this. And so counterfactual regret minimization was a way of figuring out that we could be smarter about this. And how does that work? I mean, basically, you have all of your information sets in your game, and counterfactual regret minimization is going to run one of the external or the internal regret minimizing well, it's going to run the external, actually. The external regret minimizing algorithm we have, like hedge, like we mentioned, it's going to run that at every one of the information sets. And so on the various actions that you have at that information set. And so the regret decomposition theorem is a theorem from that paper that tells us that we can do this, that basically says that we can think of CFR as a policy improvement algorithm, which is locally running an external regret minimization algorithm at every information set and sort of deciding, like, can I find a better action at this information set, sort of, thinking about my values the rest of the way down the tree as, whatever they are, just kind of in the same way that you think how policy improvement works, by making these local changes. So just running it locally, making your local updates, and having all the values sort of propagate back up as a result. So we have an efficient external regret learning algorithm for extensive form games in 2007. And we have the same kind of results, which is that, it's achieving no external regret, so therefore it's learning a minimax equilibrium in zero-sum normal form. That should say extensive form games, right? That's the whole point. Okay, so counterfactual regret minimization, big breakthrough. All right, so so that's great for zero-sum games. Now, what about general sum, non-zero sum games? So the problem, again, is that we can't just go from our nice compact representation to the normal form representation and minimize internal regret as we would hope to do in extensive form games, because that's exponential blow up and there are just too many deviations to consider. So in a very nice paper by von Stengel and Ford in 2008, they proposed a couple of restrictions. So restrictions on the possible deviations for extensive form games in attempt to actually make it so that we could efficiently compute some notion of correlated equilibrium in extensive form games. And so they propose two types of deviations, which I will probably talk about in more detail later. And so, but just so you know, one is called behavioral deviations, one is called causal deviations, and they propose corresponding notions of correlated equilibrium for them. And so that's just because every time you have a deviation class, you get a corresponding notion of equilibrium. So that was kind of what I was saying in my 2003 paper, right? You define the phi class of deviations, and now you have the phi equilibrium that you will converge to if you minimize regret with respect to that class of deviations. So same thing here, we have the behavioral deviations, and you might say they define the behavioral extensive form, correlated equilibrium, which they called extensive form correlated equilibrium. And another idea of causal deviations, which is similar, also using behavioral deviations, something called reduced strategies. All right, so this is important because causal extensive form, well, I think I'll tell you in a moment. Yes, so this becomes important because now it's 2008, and there's this kind of breakthrough by von Stengel and Forge where they define these behavioral deviations and causal deviations, but in terms of the regret minimization community, kind of nothing happened. So it's 2008, and I don't know if we were all asleep or, I had small kids or whatever, but we didn't do too much, as far as I'm aware, on this problem for quite some time. And then, voila, in 2020, Chelly et al. Developed a very nice learning algorithm called ICFR, which I think might be informed or internal, maybe internal CFR, I'm not sure. Okay, that minimizes causal regret. So in other words, they were able finally to come up with an efficient algorithm that could learn a notion of correlated equilibrium in extensive form games. Okay, and that was a best paper. So that was quite nice after sort of a decade hiatus, as far as I know, in development. All right, so what are we presenting? What are we doing? So what our goal was to sort of mimic my 2003 paper with a broad class of algorithms or a broad class of deviations, of phi deviations that we could minimize regret with respect to, and then learn the corresponding class of phi equilibria for extensive form games, and to do that efficiently. Okay, so remember, we know that internal converge to correlated, external converge to coarse correlated, all that, but we want this all along one continuum. So that is exactly what our recent ICML and AAAI papers have done, they've introduced something called extensive form regret minimization, where you give it a choice of fee, and it will give you an efficient no fee regret algorithm or fee regret minimizing algorithm for extensive form games. That is our main contribution, and it is nice. It's nice. It generalizes CFR. It generalizes ICFR. Basically, you just have to choose the fee to be the corresponding set of deviations, and you will recover those algorithms. So we're quite excited about this. We think that it opens the door to learning, in non-zero sum games and extensive form games. So just, we play poker very well right now. And so what games, Hanabi or Diplomacy or Stratego, whatever, what games are we going to be able to play now that we have extensive form regret minimization? All right, maybe, okay, now I'm ready to give the outline of the talk. I realize that I'm looking only at my slides. I have no idea what time it is. And the talk history is over, but maybe we could pause for questions, and maybe if someone could tell me what time it is. That would be great.
You still have more than half an hour.
Okay. All right. That's not too much time, but okay. Anybody have any questions about what the point is, where we're going? All right. I can't see if anyone has any questions, so just
I'll
chime
help
in
you
and interrupt me if there are questions.
Yeah.
But hopefully everybody gets my big picture.
Yeah. There is a question now, actually.
Okay, great.
Bernhard.
Hi. So this is thanks, Amy. So I'm Bernhard von Stengel from the one of the people you just cited. So you will, I guess, explain a little bit more about the fee that you construct for the extensive form correlated equilibrium. Okay, so I'll just wait. Thank you.
Yes, it's coming. It's coming. That's sort of the big story, but it's coming.
Yeah,
I hope I have enough time. Okay, so we've done the literature survey. We were through point 1. All right, so I want to quickly define internal and external regret and tell everyone what coarse and correlated equilibria are. I want to define regret matching, which is a nice general fee minimizing regret algorithm. I want to briefly tell you about time selection, and then I will get to Bernard's question. I want to define all of the deviations, and there will be a few notable subclasses such as counterfactual and causal and a few others, and then hopefully show you the algorithm if we have time. Okay. I hope everybody's free till 11:30 or whatever in your time zone is. 1 more hour, okay? All right, so here is the game of chicken again. I think we're familiar with this. So let's make sure everyone knows what a correlated equilibrium is. Correlated equilibrium is a joint distribution over the set of action profiles. So that means that it will put probability on these various cells. So it could be, for example, a quarter probability down here and a half probability up here and a quarter probability over here and no probability on dare, for example. So that's a joint distribution over action profiles. And now the way to think about a correlated equilibrium, it is a joint distribution, but the way we often think about it is in terms of a mediator who gives the players recommendations. Now, just to be clear, you don't need a mediator to implement a correlated equilibrium, but it's a nice way to think about them. And so what we think of is that the mediator gives a recommendation, in this case, it's going to be AI down here, to the players. And then the players get to condition on that recommendation. So conditioned on that recommendation, there's some probability distribution over what the other players are doing. And now a player is going to be in a correlated equilibrium if for all of their recommendations, and they do this conditioning, the utility that they get for following the recommendation is better, that's AI over here, is better than the utility for AI prime over here doing something else, so not following the recommendation. So just very quickly, here's an example of a correlated equilibrium in this game. It's a third, a third, a third. And so if you get the recommendation chicken, if let's say on player 1, I get the recommendation chicken and it's a third, a third, a third, I know for sure that I know that the opponent is playing half chicken and half dare. That's my inference that I get to do from a third, a third, a third. And so I'm going to be happy following my recommendation. Let's say my recommendation is chicken. I'm happy with the chicken recommendation because when it's half-half, I know that my utilities are going to be half 6 and half 2, which gives me a utility of 4 as compared to half 7 and half 0, which only gives me a utility of 3.5. So I'm happy to follow my recommendation. I also, if I get the recommendation dare, I know, because it's a third, a third, a third, if I get dare, I know for sure that the opponent is playing chicken. So I know the opponent is playing chicken for sure, and I don't want to deviate from the recommendation dare. So that is a correlated equilibrium. Here is a another example of a coarse correlated equilibrium. So here we don't really have the recommendations coming, but we're conditioning on the joint distribution. And you can see from this example that coarse correlated equilibrium maybe is going to be a little bit weird, because a coarse correlated equilibrium in this example, which is due to Aaron Roth, by the way, is actually a third on the diagonal cells is going to be a coarse correlated equilibrium in this example, even though it's putting a third weight on this minus 1.1, which is not a very desirable outcome. So what happens here is that if we have a third, our payoffs, or actually symmetric, so both players' payoffs are a third of 1 plus a third of 1 plus, minus or plus the negative of a third of 1.1. So we get 0.3 from playing a third. Now, alternatively, we might play just A, or we might play just B. We probably won't play C. That's all negative anyway. But if we play A, what do we get? We get a third of 1, a third of minus 1, and a third of 0. So that payoff turns out to be 0. So by following this coarse correlated equilibrium, even though it puts weight on this negative CC cell, we get a payoff of 0.3 as opposed to 0. Okay, so that's an example of a coarse correlated equilibrium. So hopefully now everybody knows what those things are. All right, now we go to my slides from 2003. Oh, by the way, I should say that Dustin has made many of these slides, and wait till you see them, especially when we come to Bernard's question, because they're quite beautiful. This is an example of a not beautiful slide made by me. All right. So here we are. Now I want to explain to you what the deviations were in extensive form, in normal form games. All right, so we can think in a normal form game that we have a bunch of actions and we can transform our actions. So there are various ways that we might transform actions. So deviation is a function from actions to actions. So here's the first example. These are the external deviations. What they do is no matter what action this function is given, it will transform to some other fixed action. So this function is transforming to fixed action A. And so when I write E sub A, that's the basis vector with a 1 in the 8th component. Okay, so I'm just thinking of my strategies. Oh, well, I guess this should be delta A up here, right? I'm thinking of my strategies as probability distributions over my actions. So, so the external transformations transform anything to some fixed action. The internal transformations, well, there's one for all possible pairs of actions, A and B. And so this one, this phi AB, when it gets the input A, it transforms to B. So only when it sees the input A does it transform to B. Everything else, no change. Okay, and in general, the set of all possible action transformations that you might have here, there are n to the n of those where n is the number of actions, and they are called the set phi swap. So when I mentioned earlier that phi internal was kind of the largest set that's of interest in normal form games because it converges to correlated equilibrium and you can't do any better. You might have tried throwing in more deviations from the set phi swap, but it doesn't get you any additional power. All right, so I like to think about these deviations as stochastic matrices. So here's a picture of them written this way. So what this says is that the phi 2x is saying no matter what, I'm going to play action 2. So you can think of your inputs kind of coming in each of these columns. Like if I were recommended 1, I would switch to 2. And if I were recommended 2, well, I'm already at 2. If I were recommended 3, I'd switch to 2, and so on. Internal regret, similar. So again, this is saying if I am thinking about playing action 2, well, let me switch to 3. That's what this particular internal regret matrix is showing us. And we have the identity. We have 1s on the identity everywhere. So that's just saying, you know, don't make any other changes except for 2 to 3. And we would have an internal regret matrix. We'd have n squared, order n squared internal regret matrices because we can switch from, you know, any action to any other action. And just a little bit of matrix algebra here shows you that if you take, you know, the external matrix over here, you multiply it by some input vector, you end up with all your weight on 1 if it's the 2, right? Because we have all 1s in the 2 row over here. Okay, and likewise, the phi internal, what do? They take all the weight that you had on 2 and they move it to 3. And that's what well, I can't seem to highlight the right things, but that's what you see here. Okay, great. So why do I like to think about deviations as stochastic matrices? Well, the reason is because we have a really nice regret matching algorithm which uses this formulation. So how does that work? Well, imagine that we're in phi space, so that's our set of possible deviations. And we have a current regret vector that's in this phi space. We'll look only at the positive parts of the regret vector. We'll ignore the negative parts because, we want to know, what do I have regret for? And we want to think about playing for the things, putting positive weights, starting to play things that we regret not playing before. Okay, so the way that this algorithm works is basically you imagine that you have all of those matrices. So I have a bunch of phi matrices, all those stochastic matrices that are thinking about all the different ways that I can transform my actions. And what I'm going to do is I'm going to use as a coefficient in front. I'm going to take a convex combination of all of those stochastic matrices, but I'll use as my coefficient how much regret I have for not using that transformation. Okay, so I have my whole set of, let's say it's the internal, so I'll have n squared of those stochastic matrices I just showed you, and I have regret for not playing each one of them. So the regret I have for not playing each one of them becomes the coefficient in this new stochastic matrix that I am going to build. So this is a convex combination. We're normalizing by our total regrets, and we're, in each of these, we're putting a coefficient in front of that particular transformation, saying how much I regret not playing that transformation. Okay, so that's how we build this stochastic matrix, and then it turns out that playing the fixed point, oh, whoops, I switched from left to right multiplication. This should say pi equals a pi. Okay, but anyway, playing the fixed point of this stochastic matrix, that is going to be a regret minimizing algorithm. That's a regret minimizing algorithm. All right, so hopefully that's clear. That's regret matching. That's what we knew in 2003 as a nice algorithm for minimizing internal and external regret in normal form games. I actually think I had better skip the proof because in the interest of time of regret matching, but I will just tell you that it minimizes regret. The key is Blackwell's approachability condition. And basically by choosing this fixed point, we can satisfy the condition required to minimize regret. Okay, great. So, so one more concept we need before we can get into our new stuff, and that is the idea of time selection regret minimization.
We have one more question, Amy.
Oh, wait,
is that okay?
Yeah. Yes, please.
Yeah, sorry,
it's always okay. Yes, please.
It's me again. So there is also in fact, I mean, the Hart-Schmeidler proof for the existence of a correlated equilibrium assumes, in fact, from which much of this internal regret thing stems from, it was also then used by Papadimitriou and Roughgarden to develop an algorithm for computing a correlated equilibrium. Mm-hmm. Does the following: it assumes that you can profitably deviate, by some, and then it uses a neutralizing mixed strategy for each player that proves that this is not profitable, and thereby produces a proof of the existence of a correlated equilibrium. So I wonder if, in case you know this, is that the same thing, this neutralizing thing in the fixed point that you just exposed, or is it something different? You don't know. I think it's very interesting. It's a very interesting question because it's very similar, and so I think it's worth looking at.
Definitely worth looking at. Yeah, definitely.
Yeah, okay, we can do that. Maybe sometime.
I've looked at other proofs of other things, and I can often find them, kind of map them onto my intuition, which is the one I just presented. So I wouldn't be surprised, but we should look.
Yeah, we can talk at sure, some other time.
I would
sure,
like to.
Sorry.
Yeah. Great. No, it's good. No, please interrupt so I'm reminded that people are there, and so I can get a time update. How much time now?
About 20 minutes.
Okay, thank you. All right. Okay, so one more quick concept: time selection regret minimization. So another idea dating back, 20 years. Okay, so here we imagine that we're minimizing regret, but we have what are called time selection functions, and they tell us sort of which, we have a bunch of these time selection functions. They tell us which rounds we care about during our learning, or which days. Sometimes I think of them as days. So the first one, W1, like we just care about everything equally. We have weight 1 on every single day, and this is just our usual, utility calculation. But it could be that we only care about even days, say. And we want to, make sure we minimize regret on even days. Or it could be that we care about day 1 a lot, and we're kind of decreasing how much we care about all of the various different days. Basically, we can have arbitrary weights on our days, and we can compute weighted utilities given these time selection functions. And so what time selection regret minimization can do for us is it says that for some finite set here of weights, for all of the weights in this set, we can minimize this kind of weighted, we can achieve no regret with respect to this kind of weighted utility. So we have the same, maximizing over all of our fees, and everything in terms of just weighted utilities. But what's interesting is, for every one of these weights, we can pick a fee that's going to be the best fee for those weights, and we are going to be doing as well as all, for all of the W's, for all of our different time selection functions, we will be able to minimize regret with, one learner that's learning to do as well as all of these different time selection functions, right? So it can do very well on even days, and it can do very well on odd days. And each of those days gets to, pick the best expert. Well, sometimes we think of them as experts. Pick the best deviation or expert to compare itself to on each of those days. Okay, so that's time selection regret minimization. Again, there are algorithms that do that. I sort of have a, just ignore if that's saying that Blackwell is still going to work in a slightly modified way where we have to, sum up over all the weights, composing the stochastic matrix as I was describing before, but with lots of sums over weights along the way. Okay, great. That's our background, 40 minutes in. All right, we already saw this game. Great. So now we're going to start looking at the space of deviations in extensive form games, and we're going to see that it's much, much greater and more complicated than it was in normal form games. All right, so here we have an extensive form game. Here we have another nice thing in Dustin's thesis, which he's defined something called partially observable history processes. I encourage you to read his thesis when it's out. What he's doing here is, this is an extensive form game, and he's just saying that from the point of view of any one of the players, we just fold everything else into the environment. I think we all know that you do that when you're actually building these learners for these games, but this is a nice formalism in which to talk about that. So here in this picture, you see that like player one's, he calls it a pop. Player one's pop is, over here, it just pays attention to player one's information sets, and player two's pop is over here, just, paying attention to player two's information sets. So those are the places where player one or player two has to make decisions. So now with this pop formalism, we can think about deviations in extensive form games. So here's a picture of what things might look like from the point of view of one player. And for this particular, we have 5 information sets here and maybe 2 actions at each. Maybe there are 32 different strategies here. And if we think about all the different ways that we can transform these 32 strategies into 32 other strategies, we're going to end up with too many deviation functions. And in particular, these 32s have the number of information sets here is 5. And so you can see we have kind of 2x doubly exponential here. We have, too many because we're exponential twice here in the number of information sets. So we don't want so many. So what are we going to do? We're going to call up our friend Bernard, who is, asking all our questions here because he's responsible for an important idea about how we're going to manage ourselves in this situation where there are just far too many deviations to think about. And so the idea is the following. The idea of behavioral deviations. It says, let's look at our, when we do our conditioning, let's not condition on anything that could happen like later on in the game. So we'll be proceeding along in a game and we've gotten, say, a sequence of recommendations, and we're only going to be allowed to look at earlier recommendations in the game. So in general, in this picture, I'm doing any transformation to any strategy to any other strategy. So you imagine you're given, even up here at the top of the game, maybe I'm giving a recommendation, which is a full strategy. So Bernard's going to say, no, you're not allowed to do that. You can't give me up here at the beginning of the game a recommendation, which is a full strategy, because that's giving me more information about things that are happening later, which of course would be helpful, and we would learn correlated equilibrium with that information. But that's too expensive. So when I'm like here in the tree, I can only look at recommendations that arrived earlier. I can only condition on earlier information. That's the idea of behavioral deviations. And just to mention, he also introduced the idea of reduced strategies, which meant that after you deviate, you got no further information. And again, just to remind you, that's the kind of strategies and the kind of equilibrium that Celli et al. Were studying in their Nervous paper. Okay, but just following along with our general idea, we know that if we have behavioral deviations and we were able to minimize regret with respect to behavioral deviations, we would have a behavioral equilibrium, or what Bernard called an extensive form correlated equilibrium. And if we use the reduced strategies, they're now called causal, or maybe just extensive form. The language is a little muddled between the AI community and Bernard's original language. Okay, so that's the key idea. And now to answer Bernard's earlier question, partially anyway, here's a picture of what behavioral deviations in extensive form games look like, and it's much more complicated than what we had in normal form games. So in normal form games, we had the stuff at the top and at the bottom, right? We had internal and we had external. We didn't have all of these other intermediate setups. So up here is behavioral, what Bernard defined, and there are still quite a lot of behavioral deviations. So our algorithm will work, but there, may not be super effective or efficient, in particular, because here's the numbers of deviations in this picture, and we still have an exponent in the depth here, although we're linear in the number of information sets. All right, so let me explain this picture. So first of all, we have trees, and an internal deviation is we take the whole entire strategy, the whole strategy throughout the whole tree, and transform it to something else in the same way we saw with our stochastic matrices earlier. External down here at the bottom, it's like this, just transform to a fixed alternative strategy. Okay, so those are our, and so when they're red, that's a deviation, and when they're blue, that is a recommendation. And then you can also use what we call the identity transformation, which just means you follow along with the recommendations. You just go with the recommendations, you follow them. Here we have how we're drawing sequences, and here are pictures of actions. All right, so let's start with counterfactual, say. So counterfactual, first of all, the nice thing about counterfactual is that there are only going to be n times the number of information set number of counterfactual deviations. And the big theorem and the big success of CFR is that if we think about external, there are n to the I of those, right? We're thinking about all the different strategies that we could be transforming to in an extensive form game, and that's going to be, in general, there are many of them. But counterfactual regret is kind of miraculous because it only has to look at n times, a linear number of information sets, and it can still minimize external regret, which would have, you think of as having it being exponential in the number of information sets. Okay, so what do these look like? The way we think about counterfactual deviations now, not the way that Marty and Mike introduced them years ago, but the way we think about them now is that we deviate straight to some information set. We just play head on straight to an information set, and then from that point on, we follow recommendations. So we deviate and then we follow. That's sort of the picture for counterfactual. And we might do that getting a recommendation first, right before we join and follow. And that's what we call informed counterfactual, or we might do that in a blind sense, which is the way the counterfactual was originally implemented, which is there were no recommendations. We just kind of, start following once we get there. So again, just to remind you, I was sort of alluding to policy improvement and policy iteration improvement algorithms before, and that you could sort of see that from this picture if you knew how to interpret this picture, which is, you're following after the fact. So you're going to make a local improvement, and then you're using your policy that you have after that, right? So you might make a local improvement right here by running a regret matching algorithm locally where we are at this moment to see, which of my actions can improve what I'm doing right now, assuming that counterfactual values, which means assuming I'm following the policy as it is ever after. Okay, so that's, if you know the counterfactual algorithm, regret minimization algorithm, hopefully that made sense with this picture. So in contrast, we could do the opposite. We could follow first and then deviate. So this is causal. So causal is going to mean we follow, maybe we get a recommendation, maybe we're informed here, and then we go ahead and deviate. And this is actually causal in the reduced sense, where we're not getting any further recommendations. We're not getting any reduced strategy sense. No further recommendations. Once we deviate, then we're on our own, and we just have to figure out the best kind of external, the best fixed strategy to play ever after. And so Bernard and Francoise in their original paper also defined something called, I think they defined this, they defined agent form correlated equilibrium, which I'm pretty sure corresponds to these action changes. So you can see what this picture is, right? You follow for a while, and then you're going to deviate once, and then you start following again. Okay, so follow, maybe get a recommendation, and then deviate, and then follow again. So this is the space, a part of the space anyway, of behavioral deviations in extensive form games. And our idea is to look at this space and to build EFR, which is an extensive form regret minimization algorithm, which is going to work for whichever set of deviations we input to it. Any set of deviations we give it, the algorithm is going to minimize regret with respect to that set of deviations. That's the objective. So hopefully that's clear. And then, of course, if we can succeed at that, I mean, we did succeed at that, but then we are learning the corresponding notion of equilibrium. So we might be learning counterfactual correlated equilibria or causal correlated equilibria. Depending on the set of deviations we give, that's the set of equilibria that we learn. Okay, and you can see, by the way, we have the same results from before, which is that internal would correspond to correlated and external to coarse correlated. So external is the weakest, so coarse correlated is the largest set here. If you learn down here, coarse correlated, that's the largest set of equilibria you can learn. And causal, counterfactual, those are stronger than external. So if you minimize regret with respect to either of those, you have minimized regret with respect to external. And you can see that kind of from these, well, you can see that from the causal picture, and we know that from the regret decomposition theorem in the original CFR paper. Okay.
Amy, just a quick update. We're just below 10 minutes left.
Okay, that's unfortunate because I have a lot more to tell you. Okay, but hopefully you are learning something from what I've said so far. All right, so let me go through a few examples now to show you that causal and counterfactual are incomparable. So they both imply coarse correlated equilibria, but they themselves are incomparable. So here's a couple of examples. So here we have something that is a causal equilibrium and not a counterfactual action or behavioral, even coarse correlated equilibrium. Okay, so Battle of the Sexes. Hopefully many of us are familiar with this game. We have these two people who, like to coordinate, but one likes X better and one likes Y better. So the game here is that there's a free upgrade available. One of the players can go and just, if they want to, go ahead and get an upgrade. And if they get the upgrade, then the payoffs become 3 and 2 instead of 2 and 1. Right? The upgrade just allows you for free to just get higher payoffs. So the point of this example is to show you that actually this is not getting the upgrade. Not getting the upgrade is a causal correlated equilibrium, but of course not getting the upgrade is kind of a dumb thing to do, right? You might as well go get your free upgrade. And so here we're drawing a picture, we're just showing that there is a beneficial counterfactual deviation, but it turns out that there's no beneficial causal deviation. And so I'm anxious about time. I don't know how much time I should spend, but let's just leave that for 1 minute and we'll try the matching pennies example. So here's another example. So this is matching pennies. And now we have a situation which is a counterfactual. So it's going to be another situation where, there's kind of an obvious thing to do. And the counterfactual equilibrium is sorry. So there's the causal, we're not going to be in a causal equilibrium because there's going to be a beneficial causal deviation. There's going to be something that you obviously should be doing, and the causal deviations will figure it out, but the counterfactual deviations won't. So what I'm showing in these slides is only beneficial deviations. I'm not showing you the many, many deviations that are not beneficial. So in other words, to show that this is a causal equilibrium, this thing that I'm showing above the line here, to show that that's a causal equilibrium, I'd have to show you something like 16 different causal deviations and that none of them are beneficial, right? And likewise for this example, for all the counterfactual deviations. So let's look at this example in a little more detail. So this is matching pennies. And hopefully some of you are familiar with this game as well. One player wants to match and the other player wants to mismatch. It's a zero-sum game, so we have just one payoff in each of the cells. So in this game, player one gets to decide in advance if they want to match or if they don't want to match. So player one just decides upfront, match or don't match. And player one knows what they've decided. So if player one decides to match, then then of course they know that, and so they should go ahead and match player 2. So the way a correlated equilibrium works is that depending on the recommendation that you get to condition on that information, like we saw in the earlier example. And so in particular in this example, when player 1 gets the recommendation, in this recommendation 1, when player 1 gets the recommendation don't match, player 1 can infer from the don't match recommendation that they're in recommendation 1 and that player 2 is playing heads. So they infer don't match and that player 2 is playing heads. And so then, of course, what player 1 should do is go ahead and play. Don't match, right? So of course they should play tails, and they're happy. So that's good. That's good in this case. In this situation, in recommendation 2, when player 2 has gotten the recommendation to match, player 2 knows we're in this situation. So when they see that we're matching, they know player 2 is playing tails. So player 2 is playing tails when we're matching. And so, of course, because player 1 knows that it's match, player 1 should play tails. Player 1 should not go ahead and play heads. So what this example is showing is that the counterfactual deviations couldn't figure this out. The counterfactual deviations are still over here following these recommendations and deciding, okay, well, it's just fine. Even though I got the recommendation match, I should just continue and play heads, even though I know that the other player is playing tails. Okay, so hopefully I conveyed to you that that's a silly thing to do, but the counterfactual deviation couldn't figure it out. And in the early example of Battle of the Sexes, the silly thing to do was to not take the upgrade, but the causal deviation couldn't figure it out. And these pictures show you what the beneficial causal deviation is, or counterfactual, that the deviations have figured it out. Okay, so sorry if that was a little bit fast, but here we have a more complicated kind of recommendations that are coming, because the recommendations are, for the whole, throughout this whole tree of what we should do. But it's the same idea we saw with chicken and dare, the same idea we saw earlier, which is like from the information, when I got the recommendation not match, I know which of these two scenarios I'm in. And so I can use that information from not match to figure out, okay, great, the other guy is heads and I should be tails. Or when I get the recommendation match, I should figure out, okay, good, the other guy is tails, so I should be tails too, right? As the causal deviation is able to figure out. Okay, great. So what does our algorithm do? Well, I have probably only 5 minutes left, so I probably don't have too much time to do it justice. But very quickly, what the algorithm does is it will take the deviations that, whatever the set of deviations is, that we want to minimize with respect to, and it will encode those deviations as time selection functions. So it will use the idea of time selection to encode deviations so that it can determine which of the situations it's in. Like, am I in the not match situation or am I in the match situation? And so again, we're only looking at behavioral deviations. So we can only look at information above us in the tree. But you can kind of see in this example, when I get down here to this red node over here, I know the recommendation I got beforehand. I know that I got not match, right? So I know what I saw beforehand, or I know that I got match, and so I can use that information, condition on that information, and that gives me a hint as to which of these situations I'm in. And I can use that information to basically to wake up some nodes and put other nodes to sleep at various times, or to do them, not maybe 0, 1, maybe with different weights, so that we can apply the time selection idea. So what we're seeing here is we're seeing a matrix that we've created for this example using actually all the behavioral deviations in this example, and us using with them the corresponding time selection functions, which tell us under certain recommendations that we should wake up some of these time selection functions, and under the other recommendation, we should wake up other time selection functions. So one important thing to notice is that this middle column is counterfactual deviations. So the counterfactual deviations don't really pay attention to any recommendations, and they just deviate in this kind of like, let's just switch to some, one or the other strategies. Let's just go ahead and switch. So counterfactual deviations just all have weights 1, and that's why we never paid attention to time selection or anything in the past when we were working with counterfactual deviations, because it's not really doing anything. And if you look So here are the various recommendations we might have gotten. And here are the transformations that we're considering from heads to tails or tails to heads in this case. And the counterfactual deviations are the ones in green here. And if you sum total them, you see that we have no counterfactual regret in this example. So in this example, I said that we would be at a counterfactual equilibrium. The counterfactual deviations can't figure out that they should have followed, they should have done something different here. In contrast, the causal deviations, when we look at the regret associated with the causal deviations, we're going to find, which are these other ones, we're going to find that, or not just causal, any behavioral actually, all the behavioral, we're going to find that we actually, need to pay attention to the fact that we have regret under recommendation 2 for this time selection function, the corresponding time selection function. So the idea is that we can encode the information in the deviations in time selection functions. And basically, we can therefore run time selection regret minimization at every one of the information sets, which is a generalization of running just regret minimization as we were doing in CFR. So we run time selection regret minimization at every one of the information sets, and we choose the time selection function. So it's very important. When I showed you the slide with the time selection, all of those W's, they were exogenous. They were all just kind of given to us. So it's very important, the insight that the behavioral deviations only use information above us in the tree. That's very important because that means when we're building these time selection functions that we have the information we need from the recommendations that we got so far in the tree. So we build the time selection functions using that information, and then we can run time selection sort of at the next information set in the tree. So key idea of the algorithm is to run time selection regret minimization at every information set, building time selection functions as a function of the deviations that are input to the algorithm that sort of tell you how to build the time selection functions for that deviation set. And with that whole story, we get convergence to the corresponding type of equilibrium, depending on the types of deviations that were input to the algorithm. So now speed by.
We have gone through the time, but okay. I don't think.
Two minutes?
We can go a few minutes over.
2 more minutes. I'm really sorry. Yeah.
No worries.
First of all, I showed you a picture of deviations earlier, and there were fewer than we've really investigated. So there are more. So now you have a very terrible, ugly picture of more deviations. But I want you to notice in particular twice informed. So behavioral really, remember, still had an exponent. It had a D and an exponent. None of these have any exponents, so that's good. And twice informed is kind of our favorite contender at the moment. And this is just very quickly some experiments with these different deviations. And so regret minimizing algorithms that can minimize all of these different types of regret. And so we can have, we looked at 3 different games here, or we're showing 3 games here. Dustin's experimented with many more than just 3, all from OpenSpiel in 2 different settings. One setting had a fixed opponent, and one had a learning opponent. In the fixed opponent setting, we played the agents first in self-play against themselves and let that stabilize, and then kind of fix the opponent at whatever it was, and then introduced a new learner to play against the fixed opponent in that class. And so what you see here is, first of all, behavioral, which is the strongest, is the black line at the top. Second is our preferred, which is tips, which is more efficient than the behavioral. It's the blue line. And then you see CFR, which is the pink line, which is actually doing surprisingly well in these experiments. CFR is really doing very well. I mean, we did so much work, and then, CFR is pretty good anyway for these examples. The only one that's not doing that well is the action setup, and so that's just a little bit weaker. That was kind of off to the side in our pictures. But these results are, I think, promising and interesting. I mean, they show that tips is doing nearly as well as behavioral, and also that CFR is pretty darn strong. We also did this in a learning setting where we played kind of a round robin setup against a variety of, all the other types of learners. And the results are kind of comparable, showing the same sort of improvement for basically the takeaway should be we favor tips. We think tips is the algorithm of choice, but there are many, many algorithms in this class to think about and to experiment with. And I'll just end by saying that, we haven't scaled this up yet. We would like to scale this up. That's kind of next on our agenda, but we hope that EFR can be as successful as CFR has been. Once we do the appropriate scaling up with, kinds of regression and variance reduction and sampling and all the usual things that we do to make CFR work really, really well at scale. Okay, I'll stop there. Hopefully I'm not too far over.
No, not too far.
Okay.
Thanks a lot, Amy. It was a great, inspiring, and educational talk. So many thanks for that. And I think we could have gone on for a little.
I have much more to say. I have a lot more to say. But
I don't know. Maybe okay. Maybe we have still time for the people who want to stay for a few questions.
I don't know how to get out of this. I want to see you all, but I don't know how to do that. How do I find you? Not like that. Oh,
let me.
I just accidentally closed the.
I think it's fine. Fine. Right.
Good.
But I think there's a question by Kevin. Is Kevin here?
Thank you all for staying so late. I'm sorry I ran over.
No worries. Kevin, do you want to ask your question?
Hey, yeah. So I was just wondering, in the last slide, the charts, the CFR, was that just the standard vanilla CFR, or was it like CFR plus or something?
Vanilla. Yeah.
Okay, thanks.
Yeah. Werner, do you have a question?
Yeah, so first of all, I think so very nice and very informative for me, in fact, in seeing all the way this work has been considered. And maybe there are some experts here. On extensive form learning and correlated equilibrium, we could meet separately, I would suggest, because it's a complicated subject and so on. So I would suggest that taking some of this offline. Online, but not in this group. But here's one basic question. So I hope that maybe we can exchange emails or something. But the main question that I have, what is the role of recommendations in learning? Because you mentioned that you had these light blue recommendation things.
Yeah.
I thought the recommendations come up implicitly when you learn. Where do they come from? You understand what I'm asking?
Yeah, I think I failed to, okay. So when on the little matrix that I filled in with the time selection functions, so the way we get those values that we fill in for the time selection functions come from, I might have called them recommendations, but they're not really the recommendations. They come from the strategy that we're playing, right? So the strategy that we're playing implicitly, like we're recommending it to ourselves, right? It's the strategy that we're playing, which we eventually will be correlated with the opponent's strategy. So eventually should encode the information that we think of as recommendations. Does that make sense? Does that answer?
So it's not the thing that we think we should now, the action that we think that we should now take given the history? That the one that minimizes my
well, it could be. It could be, because it just depends. Like in general, we have a probability distribution over what action we're going to take at any moment. If that's a pure thing and it just says, definitely go left, then it's exactly that. But in general, as we're learning, it's not going to be necessarily pure one way or the other. It's going to be some.
Yeah, it just was a question of understanding what you meant by recommendation. That was all.
Yeah,
thank you.
Yeah, I maybe wasn't very clear about it. Thanks. Yeah. But I think I agree with you 100% that we should meet offline and we should really work through some more examples to make sure we can really see exactly where the recommendations play into the time selection.
Maybe that is a great way to end then, because I see people have to leave. Thanks again so much. Really great talk, and I agree it would be nice to meet in a follow-up meeting to discuss more.
Thank you for the invitation, Carl.
Yes.
Really appreciate it.
Many thanks, Amy.
Thanks.
Bye-bye.
Okay. Bye.
Bye.
Bye.